Okay, the meeting has started to be recorded. We just have a few housekeeping things to run through first before we hand the meeting over to Oliver Grievson, our board chair and the presenter of this track until WETT2020 in next February. At the bottom of the screen there is our disclaimer. I won't read the whole thing. When we post the recording, the disclaimer will be on there. But the gist of it is that we present our events for education purposes. They should not be construed to be direct advertising or underwriting or anything that conflicts with our non-profit purpose. We are independent and impartial. The event is being recorded and will be available both on the Adobe platform and on YouTube. At that point, you will be able to enable closed captioning. So let me move our disclaimer out of the way here and do the introductions. My name's Dendra Best. I'm the Executive Director for Wastewater Education, and I'm the one that you've been communicating with. You'll see our contact information there at the bottom of the screen. The presenter today is our board chair, Oliver Grievson, who you can see at the top left of the screen, and at the bottom there is the logo for WETT2020, the Water and Wastewater Equipment Treatment and Transport Show, where this year we are presenting two tracks. One, a virtual reality demonstration of how to do an on-site inspection. But the other track is all Oliver's, and it's looking into what exactly is smart water, smart wastewater, and why people should care about this. So at this point, Oliver, I'm going to put away our splash screen and let you get started, and go take it away, Oliver.
Thank you very much, Dendra. Just to introduce myself, my name's Oliver Grievson. I'm the board chair of Wastewater Education. I'm also the executive director of Water Industry Process Automation Control, which is why you can see a logo behind me. But my day job is with a company called ZTech, who are EC&I specialists in the United Kingdom, where I act as a technical lead. Today I'm going to talk to you about sort of the basics of smart water. I think over the past few years it's been very confusing as to what it actually is. In reality, it's been going for probably the best part of 10-15 years now, and really if you ask 10, 15, 20 experts in the room, you'll get 10, 15, 20 different definitions of what it is. One of the other things I do is sit on the International Water Association panel on digital transformation. Yes, another buzzword for smart water. And there's about 30 people on that panel. And to be honest, 30 different experts, 30 different opinions. So let's look at what we mean by smart. So it is all about the wastewater environment. It's all about, I think for me personally, working in the industry, working in instrumentation in the industry, in the UK, we've always been at a point where we've split the network and the treatment works. We've split it into infrastructure. We split it into wastewater treatment works, very much guided by our regulators. Smart water, we can't do that. It's very much a system and a systematic approach, and seeing how we can best operate that system. In the UK, we have hundreds of thousands of kilometres of sewer, miles of sewer, and the same with pretty much every country out there. We can't know what's going on in that all the time. So one of the words that I'll certainly say in terms of smart water is situational awareness. but we'll get on to that a bit later. So if we go back in history, 1850s, we all know what's happening. We had Jon Snow, we had Bazalgette, and we had these great big sewers. They're absolutely marvellous feats of engineering, but it's bar the Thames water sewer at the minute, we can't do that anymore. If you think the Thames water sewer is about 20-25 miles, Bazalgette did 120 miles. And also we've got modern problems with the sewer. Fatbergs. We can deal with that from influencing customers, and you'll see the WRC in the UK have put out an influencing piece of fine to flush in terms of wipes. That per se isn't part of smart water, but it's actually about influencing how the customer behaves, and that you can do, and it's quite interesting, and we'll see that a bit later. But again, when we look at Bazalgette, all his piece was it actually just transferred that wastewater further downstream, and at the end of the day, there wasn't really the processes to sort out. We jumped forward 150 years, and we're in a completely different place. But again, we've got climate change. But when we look back at what Bazalgette did and the engineering, it's quite amazing. It's amazing to see what Bazalgette did. You're seeing a picture of one of Bazalgette's steam engines. If you've never been to Crossness, I suggest you do. Crossness pumping station. I do suggest you going there, because there was some feats of perfect engineering, and at the time that was actually quite smart what they did. But to get on to the subject, what is smart water? If you're in the wastewater side of the industry or the water side of the industry, you'll have heard lots and lots of terms, lots and lots of buzzwords. Smart water, water 4.0, digital transformation. Smart water is a phrase that's been going on probably for the past 15-20 years. Water 4.0 actually came from Industry 4.0, which was a French term. Actually, it was the German Water Partnership who took the French's Industry 4.0 and coined Water 4.0. Very much though, when you look at what they did, it was very much around the levels of looking at data, looking at visualizing data, looking at analytics of data. But before that, we've got to look at something else. Now the buzzword's digital transformation. And under these headings, we've got other buzzwords like big data, small information, digital twin. And to be honest, there was a presentation at the last IWA World Water Congress, and you had Patrick Decker of Xylem said, don't give me any more buzzwords. Let's just get on and do something. And it is the case, because at the end of the day, we can get very confused in buzzwords and actually struggle to know what they mean, and it just delays things and delays and delays and delays and delays and delays. So what does it actually mean? A lot of people will be familiar with this in terms of this is the Swan layers. It came out about 10-11 years ago, and a lot of people in the smart water part of the industry are adopting these layers. They're saying, yes, the physical layer. The water industry around the world is very good at the physical layer. It's very good at laying pipes. It's very good at building concrete boxes. It's very good at putting together processes. But on top of that, whenever you get a capital scheme nowadays, even nowadays, instruments came in about the 1970s. So they've been around for the best part of 50 years, not always very reliable. But at the end of the day, they've got better and better and better. We've got intelligent instruments now. We've got instruments that will actually tell us when they're about to fail. So we can use prescriptive instrumentation. But actually what comes from the instrumentation layer is data. But when you get onto a capital project, a lot of the instrumentation is almost thought as an afterthought. What we as an industry have got to do is change our way of working there, and part of the initial design is the instrumentation control decisions. What do we actually want to achieve? And it is very much thinking of it as a network, thinking of the collection system on a wastewater treatment system, thinking of the wastewater treatment plant, and thinking how those can work together. In the past, we've typically stuck a flow meter in, dissolved oxygen, mixed liquor, maybe put some control systems around there, and there's some great control systems. But there's more that we can do. What we've got to do is think about what information we need. What can we design into a process, design into the system to tell us exactly what the state of that system is? Wastewater systems are very much an unsteady state system. And to manage those, you've got to know what you're doing. A few years ago, I said quite a phrase, which was, we've got to control what we want to control, and we've got to have the information so we can manage the rest. And that really is quite important. So really, for instrumentation, we've got to be designing what information we need to control the process, but also tell us what's going on within the system. Above that, layer 3, collection and communication, basically telemetry systems, SCADA systems, and all that sort of thing. Everyone will have heard of the Internet of Things, the industrial Internet of Things. Great. It's connecting a sensor up to a centralized system in reality. To me, the industrial Internet of Things, and this is my personal opinion, it's a communication method. Doesn't matter how we do it. Do we do it by NB-IoT? Do we do it by whatever? Do we do it by satellite? It's a communication system. Data management, display, data fusion and analysis. This is what I see a lot of within the water industry, and there's a lot of solutions, a lot of cloud-based solutions. But you're almost collecting data and analyzing data for data's sake. You've got to have some sort of process. You've got to have some sort of process insight, some systematic insight to actually get value. And when you think of it from the flip side, from top down, that's when you're going to think about what value is this smart system going to give us. The SWAN layers, is very much technology based, but actually on top of this we have the technology, we have the people. By the people I mean, what's this smart water technology going to do for the customers? So we've seen a lot of smart water meters from a domestic point of view. Actually, the companies that are putting those in are finding that they can give a better service to the customers. The data from the customers is great. You've got companies out there who will do various data analysis, and they will look at influencing the customers, influencing customer behavior to get the per capita consumption down. In some countries, that's natural. So you go to Denmark, actually the per capita consumption is very low because they're quite an environmental, but quite a environmentally frugal society. So it's natural in society. Other societies are going to be different. But also, it's the processes. By this, I don't just mean business processes, although that's part of it, but also operational processes. You can take this down to level 2. In order to get a decent level 2 layer going across a company, you need those processes. Most of the water companies have those processes. How effective they are depends upon how busy the staff are. But at the end of the day, if those processes are followed, then the instrumentation, the data that we're getting from that is right. It is intelligent smart systems. It is about managing and controlling the resource on a systematic basis. And that we've got to from my point of view, we've got to forget wastewater collection systems. We've got to forget the treatment works per se and bring them together and work on them together. We have in the UK, in the next investment period, our asset management periods, a massive programme on flow, on wastewater flow, around the flow to full treatment. And for those of you who may not be au fait with the term flow to full treatment, it's the flow passing through to the treatment works up to a certain prescribed level, up to a certain consented level, before treatment works can go to storm. So it should be in wet environments, and the treatment works will have a maximum capacity that it can cope with. There are problems with that. Not all the works in the UK are compliant. That's something that's well known. But actually, if we look at using the wastewater system more, then we can drive that compliance. We can use the wastewater system, the collection network, as a balancing system. It's not going to be perfect, and there's a lot more work to be done, especially around meteorological monitoring and predictive what a certain rainstorm is going to do to the wastewater networks. There's control algorithms, there's control structures to bring in. Other countries like Germany, they have control structures in the network. They do to a certain extent. How do we get the best value out of the wastewater collection network? And that's a way of starting to manage the system as a whole. It needs quite a bit of instrumentation, which is probably where we haven't been as an industry. But it is all about the application. Wherever you go, you'll see all sorts of smart water solutions. Tell you a secret, within the water companies, they're seen as widgets. They are technological solutions to a problem that doesn't necessarily exist. So anyone out there in the smart water world putting together smart water solution, make sure you know where it's going to be applied. A lot of people right now will be looking at the asset management plans, if they haven't already, and going, yes, leakage in the UK, massive market. Sludge is separating off into, wastewater sludge is separating off into a separate market. So it's going to have to take a more factory approach. It's going to have to be monitored more so we know the throughput. It's going to become a factory, and if you don't know your product, how can you manage it? It's the old adage of measure to manage. But equally, as I've mentioned earlier, flow, phosphorus. Now, technological solutions, instrumentation-based solutions aren't going to provide the full story. They are a tool. But if you're going to a water company, you have to know where you're going to apply it. Otherwise, you'll invest as a company in a lot of money in developing a solution that's not necessarily needed within the water industry. It may be needed elsewhere, but it's not necessarily needed in the water industry in a particular company, in a particular country. And in which case, you're going to have invested a lot of money for something that may not be bought. And that is a problem with the water industry. The water industry is getting a lot better and engaging more with the supply chain, but it can be a very difficult industry to break into. So know your application, know what problem you're going to solve, and that is quite crucial. So here we've got a particular solution I was presented with a number of years ago, and some engineers came to me and said, there are these 6 penstocks, and you can see them on the left-hand side. It's a very short distance, and on the right-hand side, there's a very short distance between the end of an activated sludge plant and the effluent penstock for that plant. The engineers who approached me on this said, there's problems with the works. These 6 lanes are losing their blankets because of uneven flow. And you can see it in the telemetry picture down there. You can see spiking of the flow coming over those penstocks. and that was actually coming into the lanes. So the spiking was causing a problem. It was causing uplift. It was causing blanket loss. Actually, that was straight into the sea. The engineers said, we want to put a flow meter on top of that penstock. And for anyone who knows flow, it's not going to work. But also, they wanted it for all 6 penstocks. And of course, what was going to happen if you put flow on each of the areas, the penstocks were going to change all the time, what we call hunting. And at the end of the day, the solution wouldn't work because you had to consider A, the practicality, B, the response time, C, the speed of flow measurement, but also, if you look at the penstocks themselves, they're the best part of 2.5 tons. They can't suddenly move. Those penstocks, you're talking movement by a few centimetres every 30, 40 seconds. So they weren't actually going to be able to do the job. So it is about application. We actually did find a solution for that particular case, but it was not measured over the penstock. But if you do have an application, this is a case study that Swan produced a number of years ago with Yarra Valley Water. And what this showed, it was a very long journey for a smart water solution. And by a smart water solution, actually some of it was very basic. It was measure, set up district management areas, measure what's going into those areas, what's going out of those areas. Yes, use sounding sticks. Yes, use a number of techniques. The actual technological solution, the final technological solution, made a relatively small difference. But at the end of the day, it was a whole suite of solutions. It was actually basic common engineering sense that delivered a lot of the savings to start off with, but actually great application. The leakage was at the best part of 50%. And yes, it went down by the end of it, down to about 12%. Not fantastic, but actually pretty good in the modern terms. But before we get too complex, what are the basics? What is smart water? We've all heard Internet of Things. We've all heard smart cities, big data, small information, data analytics, real-time control, advanced process control, smart water networks, smart wastewater networks, artificial neural networks. We're hearing about machine learning, artificial intelligence, data mining. It's mind-blowing. But really, at the end of the day, for me at least, and this is a very arguable point, it's a case of using the data that we've got, looking at the information that we need, perhaps doing a gap analysis, perhaps taking instrumentation out, looking at instruments that we don't use, prioritizing the maintenance of the instruments that we do use and we do need, and using that data correctly. Because at the very smallest, you can actually look. There's a huge amount of data, and I think I certainly put it at the UK producing about 300 million pieces of data every single day. You can't possibly look at all that. But is all that data needed? That actually says 400 million pieces of data a day, but yeah, much of a muchness. If you just put universal metering of smart water meters across Europe, you're talking billions, if not trillions, of pieces of flow meter data, which is crazy, absolutely crazy. But it pales into comparison to, say, something like the CERN reactor, which I think produces a terabyte or 2 terabytes of data every single second. For CERN, most of that data isn't used. And I think it's about 10 to 15% of the data is actually used, stored, looked at. But really, do we need all the data that we collect? Some of it, yes, some of it, no. Do we, for example, if you ever go to a control center in a rainstorm of a large water company like we have in the UK, they'll be getting thousands and thousands of alarms. Should we, and here's a challenge, and here's a very arguable challenge, should we be talking about events rather than alarms? Combining a whole load of alarms together to create an event. And some of the water companies have done that. Should we be talking about event management? Possibly. It's a question to be asked. But there is a huge amount of data that we produce. Absolutely crazy. But where does it come from? It comes from the instruments on the ground. But yes, if you install a magflow, if you install a dissolved oxygen probe, how do we use it? Yes, there are real-time control systems around dissolved oxygen. Yes, smart meters are great. Yes, smart meters themselves have allowed the water companies to more of a situational awareness with their customers and allowed the water companies to support the customers more and more. We're seeing now some of the influencing companies out there, I'm not going to mention them particularly, but they are starting to use home devices to suggest to people how that they can save water and save money off their bills. And in some ways you can think that that's quite perverse, that actually the water companies want to charge the customers less, but they do, because at the end of the day, the value of that more water in terms of water resources is actually quite a bit higher. We've all heard Sir James Bevan talking about the UK running out of water in the next 25 years. Well, in that case, yes, there's work to be done on PCC. There's work to be done on reducing the water that customers use. And of course, there's work to be done to look at leakage. And this is a massive project in the next AMP for every single water company. But it's how do we use that data? All of the water companies in the UK will have a DMA. Of course they will. How do we use that data from the DMA? How do we make sure that data is right? And yes, making sure the data is right, maintaining that instrument is absolutely vital, because it only has to be a small amount off on a large meter, and that can account for a huge amount of leakage, which may not be true. It may be meter error, and certainly that's been seen in the maintenance of DMAs, either through bad installation or maintenance problems or whatever. On the Clean Water Network, yes, it's been seen. Yes, it's a problem. Yes, some of that target next AMP is going to be done on the maintenance of instruments. Absolutely fantastic. But looking at the instrumentation life cycle, I mentioned this in a different way earlier. But when you put an instrument in, you have to ask yourself the question, what is the purpose? What am I hoping to get from this instrument? Is it a regulatory purpose? Do I have to have that instrument in place for regulatory reasons? Abstraction monitoring, wastewater discharge monitoring, etc., etc., etc. Maybe. Is it for efficiency purposes? For example, is it for operational efficiency purposes? For example, a dissolved oxygen monitor on an activated sludge plant? It's absolutely essential. We can put that into a real-time control system, and I think basically that is, as realised, about 15 to 20% energy savings through real-time control of the activated sludge plant. Is it for billing purposes? But actually, is it just for billing purposes? As we've said, we can influence the customer for PCC. We can look at the customer data, certainly on the clean water side. And again, this is work that the WRC did a number of years ago. The WRC looked at the socioeconomic discharge characteristics around the country, looked at the water meter, looked at the percentage, and yes, inner city areas which have small gardens don't use as much water for watering gardens because they don't have them. and in which case more of that water goes down the sewer. That is something that I think has come to a forefront now. It's not practical to monitor wastewater discharge, but it is practical to apply some ratios, apply some guesses. Next is, what's the application? If I just use the case study I've said just now, for a wastewater meter coming from a house, it's going to be a problem because that meter is not going to be full, and actually that restricts the technologies that you can use. If it's on a clean water network, it's going to have various permissions to be used on a clean water network. If it's on a wastewater system, the application is slightly different in terms of fouling characteristics to it being on the inlet of a wastewater treatment works and an outlet. If it's on the wastewater network, different again. All of these things need to be thought about, as does the next stage, which is, how do I install it? What do I install and how? How do I choose the technology to use? How do I install it correctly to make sure it's working? Then stage on, how do I operate and maintain it? Am I going to use a fix on fail strategy, or actually is this meter critical enough that I'm going to have an enhanced maintenance program? And then how do I replace it? In my lifetime delivering flow meter projects, I've come across installations where somebody hasn't thought 20 years down the line somebody's going to have to dig this out. That's fine for, say, a very small bore electromagnetic flow meter, sort of 50, 100 mils. That's relatively simple. But when you get up to wastewater flow meters on the collection network that are 800 mil, 900 mil, the best part of a ton in weight, you're going to need a crane, you're going to need to dig it up, potentially. That's when the costs can really, really escalate. I've certainly spent $100,000, $150,000 spent on the installation of a single flow meter. And then at the end of that cycle going, well, I'm looking at replacing this meter, but should I? What have I actually used it for in the past 10, 15, 20 years? If I haven't used it, don't install it again. If I have and it's become a vital part of the process, then yes, we will. So we've got to understand the value of instruments more and more and more. We've got to look after the instruments that we need more, but actually the instruments that we don't need is something that we can rationalise on and save. But what is that? What is the information? In terms of the smart water industry, it's a case of asking the question of going, well, what value is the information that we're going to get from this instrument? So it's a case that, in fact, is part of the people process and it's stakeholder engagement. It's a case of asking the head of a company, going, what information do you want to see every morning? And going all the way down through that company to the guys on the front line going, what information do you want to see? Doing the gap analysis, saying, well, actually, we've got that already. We just need to shuffle things around a bit. Or actually, we do need to install another instrument here to get that data source, to get that information source, to allow us to make an informed decision. And once that data and that information is valued, then at the end of the day, that instrument will get looked after. The people and the process will be followed to look after that instrument because there's a value associated to it. In the past, we've just installed instruments for the sake of it, and the value is not understood. And if the value is not understood, it doesn't get looked after. If it doesn't get looked after, people go, it doesn't work, and we fall into the trap of not using the data that we've got, and the value of instrumentation is not seen, and that means that we don't use it properly. But again, it's knowing what that is. Is it regulatory? Is it efficiency? Is it operational control? Is it alerts and alarms? Is it customer service? That all leads to the data and information for the business as a whole. But once you install the right instrumentation, you don't necessarily have to put a complex telemetry SCADA system in. Here is an example of some sites that were installed correctly, and you can see over a rectangular notch where actually you can put your hand under that and keep it dry. But you'll see on the graph that site suddenly dipped down for 4 or 5 days. What does that mean? Looking at that actually was a pollution event. If you look at the volume going through the system, it was a pollution event of several hundred cubic meters. That means something. If somebody had picked that up earlier, if there was a system in place that allowed that pollution event to be detected, guess what? You could have prevented that whole pollution event from starting in the first place. And pollution events is another big thing in the next asset management period in the UK, as it probably is around the world. We've got some incredibly tight phosphorus consents coming in. Can we reduce pollution events, stop the phosphorus from raw sewage getting into the river as much as we can by, say, enabling a smart water network to prevent phosphorus consents which are, quite frankly, 10 times lower than the old drinking water consent? That's staggering. Okay, it's an annual average in the UK, but a phosphorus consent that's 10 times lower than drinking water, or drinking water was in the old 1989-1991 regulations. But it is about getting some of the basics right. I talked about processes earlier, I talked about people earlier. These are some examples from various wastewater treatment works. You can see a couple of the 2 pictures on the either end. Flow meters situated next to valves. You can see trees growing out of V-notch weirs. You can see primary settlement tanks which are just caked in mud. You can see electromagnetic flow meter caked on the inside with that was in fact ferric oxide from ferric dosing. Why did that happen? Because of incorrect dosing, because of incorrect flow measurement, because of. That now is going to cost about 50 to £100,000 to resolve, because somebody's going to have to basically dig out the pipes and replace it. The classic there, if nobody's actually worked out what the problem is installation. That flume was actually installed backwards. It will work after a fashion, but of course, in that foreground, you've got some ferric dosing. So actually, are you going to be dosing the ferric properly? Because that flow meter isn't going to be recording properly. It's about getting the basics right. And actually, you can work out quite a lot from just looking at the basics, looking at that level 2. Is that a problem within the industry? Yes, it is. Yes, there are people out there to help with that. But actually, that basic maintenance means quite a lot. Because on a weir, on a rectangular notch weir, on an electromagnetic flow meter, these can affect the measurements and hence the data quite a lot. I've certainly heard the argument of, yes, well, we can tidy up that data at another time. We can tidy it up with algorithms. But if the basic fundamental of the data is wrong, then the smart water system, it just isn't going to work. You can put in as many level 4, level 5 solutions as you like, some visualization, some analytics, but if you've got the fundamental basis of the data is wrong, the answers that are coming out of that is going to be wrong. The old-fashioned phrase of garbage in, garbage out from 1959, and the American engineers, Corps of Engineering, that's where it came from. And if you do get garbage in through poor maintenance of instrumentation, you are going to get garbage out. And your posh, high-level, level 4, level 5 system is never going to work. It's something we've got to be very careful of in the smart water industry, because the last thing that we want is, oh, we tried that, but it doesn't really work. It's a very, very common phrase. And normally you'll find the reason it doesn't work is sometimes the poor source of the data. But it's okay in theory. Here is a case study from a number of years ago from a chap called James Harrison, who looked at the data, changed the way that they looked at it, and basically they needed a vast improvement in their problem very, very quickly. And they looked at the data, they looked at the behavior of the system by looking at the data, changed the team around, changed the people around, changed the processes around, and actually changed their performance around. What they found was a blockage timeline. And what in this particular case it was a length of dry spill. There was an accumulation of stuff within the sewer, be it whatever it is. There was a rain event. If that rain event was relatively low, then basically everything just stayed where it was. If it was relatively, and could cause a blockage because of the movement of the slow movement of the stuff in the sewer. If it was a very high rainfall event, yes, it all got washed to the wastewater treatment works. But if it was somewhere in between, and it was within a risk spot within the network that they knew from going out and cleaning sewers, then that highlighted, yes, we've got to do something about it. And then that triggered a team to go out and jet the sewer, and everything was hunky-dory. And the next dry spell. And James did amazing work and developed the blockage timeline and developed an operational response and got a huge amount of benefit from it. They basically resolved the issue. Yorkshire Water's performance was suffering and needed improvement. They were taking a cyclical approach, basically saying, okay, we'll clean this because we know we should, based upon X, Y, Z. They weren't looking at what was happening within the system. All they needed, they actually had the data within, but they needed to rearrange the way they look at it and the way they looked at designing that system, designing their process response. And that's when they developed this blockage timeline and achieved a 21% reduction in pollution incidents. Now, most water companies would go, 21% is amazing. That's fantastic. Let's keep going. What else have we got to do? And that was changing that cyclical approach. We've got something very similar, but on the clean water side, with stuff that APAL did. And they were replacing the clean water distribution network on a cyclical approach. They looked to measure, they set up their own system, and actually achieved, they went from 28% down to about 7% leakage in about 3 years, which is stunning, absolutely stunning. More recently, I've seen Andrew present again, and they noticed their leakage was going back up. And again, they did the diagnosis of where it was happening, found it was on the trunk main, and have addressed the issue. And of course, it's now heading back down. Years and years ago, 4D, a chap called Jody Cockcroft of MWH, did a project for Southern Water down at Eastney. What happened was they managed to get 2 flood events very, very close to each other. And it happened almost 20 years ago now. And 300 properties flooded, 530 is externally flooded, and the Portsmouth Naval Yard. And Portsmouth Naval Yard, of course, was a strategic defensive asset, and it was not good that that got flooded and affected the defence of the nation. So it all went to the House of Lords. It drove investment within a 3-AMP period to develop a smart wastewater network as an early warning system. It was based upon the ICM Live system, which actually most of the wastewater network models are. It used rainfall monitoring, nowcast, 9 sewer level monitors, and one of the problems with the project was installing those sewer level monitors, and it allowed Southern Water's operations to have a simple tool to see what was going to happen. It gave them advance warning of the pump systems, the pump operation, which, because they were large old diesel pumps, had to be given time to work to get up to full speed. It gave advance notice of what the operators on site needed to do. Great with weather radar. Normally weather radar is pretty much spot on about 4 hours out. So it gave people time to react. And then actually, if those actions aren't taken, it will keep on badgering at the operators. You've got to do this, you've got to do this, you've got to do this. And it was great. It improved the whole system as a whole. It protected Portsmouth, it protected the Naval Yard, which is one of the important parts, and it was brilliant. But we are really as part of one great big system. When you take the toilet to the source, it's the customer, it's the collection work, it's the treatment works. When you go from source to source, it's water treatment, it's water distribution. It again is the customer. So we do have to start thinking of the water system as a system of systems. And it's something that we are starting to do right. But at the end of the day, it is a cyclical. It is what I call the anthropogenic water cycle. It's the human impact on the water cycle, how we affect it, and how we affect the whole the system as a whole. There's some more drawings about Eastney, which will just give you, that's the pumping station. That is quite huge. And that Eastney project did look at the whole system, how to bring in the technology, the people, and the process together. And it was an incredibly smart system. But often, where is it all? Yes, with Eastney, they had a look. The sewer level monitoring was a problem. But again, we've got to treat it all. We've got to treat the whole system together and see what we can do, what we can do to play tunes within the system to get the system working as a whole. Can we, in dry weather, for example, use the sewer network with enough warning to pump forward to use it as a storage tank so that we can balance flows across the system? Can we use this basically to dampen down the peaking factors in a wastewater treatment works, dampen down the diurnal profile? Because if we do, there's a huge amount of energy savings that can be made. Here's one in particular. So that in terms of the Eastney project was the catchment. It is an island of its own. What was happening at Eastney was flow would get pumped to this pumping station, passed on to the treatment works, or stored at the storm tanks on the island. And basically, because there was a separation of the storm tanks and the treatment works, it put the system as a whole at risk, and that's why the naval base at Portsmouth got flooded. Basically, the pumps couldn't cope, everything spilled over into the system and flooded the whole area. Does that make sense? So there is basically the pumping station in more detail. So the low-level dry weather flow pumps pumped up to the sewage treatment works, the low-level storm pumps, and also pump final effluent out. So you can see it as a highly complicated pumping station that was manned 24/7. And at the end of the day, in the video, in the presentation originally, you saw those pumps underwater. So I'll go forward. Study done by Professor Butler and Fanling Meng as part of her PhD at Exeter that looked at the operational control-based permitting. And the one thing that picked this up is something where I think we as an industry should be going which is looking to control within the network, looking to control through the process to treat as much of the flow as possible. Can't always be done, and if you get a storm that goes over the capacity, then hey, okay. But the work that Fan Ling Meng did, which was absolutely fascinating, and she presented at a workshop that I was hosting, was definitely the case of, do you know what? We can get a lower cost at the treatment work for better overall environmental quality. So we can get a better outcome for less money. And if you say that to somebody, they're going to go, well, how do we do it? Unfortunately, it is difficult. And at the end of the day, here's what Fan Ling showed. But at the end of the day, it was a case of the Environment Agency brought out operational risk based on process-based control. But really, the financial benefit just wasn't there to be done, because we didn't look at all the benefits. That if we did have a operational process-based control-based permitting, then we could get a better result for less money. And that's probably where the benefit lied. Unfortunately, in the feasibility study, it didn't point out that eventuality. Maybe it's a case we look at that again. But it doesn't have to be complex. This is a case study from a works that I know very well. And smart water is not going to solve the problem, but
we have the technology for a smart water industry, but what does this actually mean in practice? We heard earlier this year in the UK, Sir James Bevan talking about the jaws of death and the water industry in the UK running out of water. What we can see in this graph is an example from a few years ago. But yes, demand outstripping supply. In this particular case, 300 megalitres per day shortfall. What we can do about this is actually probably a multifaceted approach. This case study is one I mentioned earlier, is from Lisbon and the City of Portugal, and was delivered by Andrew Donnelly and the local water company, IPAL. In this, we see that previous to this example, leakage in the city of Lisbon was around 23 to 25%, and this had held for about 8 years. What they did in Lisbon was actually find out where the main problems were, and instead of taking asset replacement strategy, changing that strategy to replace where needed. And in this particular case, we can see in a matter of 8 years, leakage in the city of Lisbon shrank from 23.5% down to 7.9%. Subsequently to this, in a presentation earlier this year, Andrew Donnelly presented that things had crept back up. But they found the root cause of the problem was mainly on the trunk mains, and in so addressed the problem, and again the leakage percentages were back down. So this is using the data that we have within the water industry to a good extent and finding out where the problem is, rather than just taking a routine replacement asset management strategy. But actually leakage reduction isn't enough. And this is where we've got to look at how we can use AMR, how we can use AMI, how we can use smart meters to address the problems of, like customer side leakage, which we know as an industry is a massive problem, but also per capita consumption. In the UK, our per capita consumption is around 140 to 145 litres per head per day. Other countries much higher. Where you have it much lower, in countries such as Denmark, it's because there is a culture that doesn't allow the wastage of water. If you haven't got that naturally within your culture, then there's work that can be done using smart water meter data and influencing customers to get leakage, to get reductions in the consumption, And this we can see in the next case study. This was something done with Angling Water in their shop window and a company called Adviso. And as we can see, 4,500 properties in the trial, 18,500 litres of water per day saved, and a roughly an 8% reduction in leakage in per capita consumption rather than leakage over that time period. It isn't just per capita consumption, it isn't just customer side leakage, it isn't just the leakage that the water companies are responsible for. It's actually a combination of a variety of different sources that the industry is going to have to look at. And this is where the smart water industry becomes a tool to drive this together. We've come a very, very long way since Bazalgette. We can no longer build giant sewers. We can no longer build 120 miles of triple line brick sewer as Sir Joseph Bazalgette did. Coincidentally, we are, of course, doing that with the London Tideway project. But that is an exception rather than a rule. We've got to look at how we can not just deliver something from an infrastructure point of view, but deliver it in operational management. And that is where the smart water industry really comes to its forefront. So to come onto this is a sort of taster for the WETT show, which is going on in February in 2020 over in Indianapolis. And I do hope that you can all join us there. Over the next few months, Wastewater Education are going to be hosting a program of webinars for people to get a taster of what's going to be happening out in Indianapolis. So keep an eye out. The next webinar is on the 18th of September, and is Dr. Corinne Carpentier from Sensilo, who is going to talk about the Sensilo database, which is a resource not just trying to tell people about products, but trying to tell people about the principles. So thank you very much for joining us today. It's been a great pleasure, and I hope you've enjoyed it. So please share this if possible, and have a good evening. Thank you. Good night.
One of the issues I'm sure that video raises is the last few seconds of the impact on municipal systems, on water, power, electricity. If people in the US are remembering this, you can remember that Sandy impacted most of the eastern seaboard. Anybody that lives in a coastal or a riverside community is going to have to pay real strong attention to smart water and smart wastewater control systems, because the need for them is already here. Do you have any final comments, Oliver? Don't see any. The Sinking Cities series, and I'll put that into the chat window too, is a 4-part event. You can find it on pbs.org. It is also streamed on Amazon Prime, and you can purchase the DVD from Amazon as well. And it addressed New York, Tokyo, Miami, and London. And we will be showing short clips of that in our upcoming events as well. So with that, ladies and gentlemen, I think we're going to end the recording. If anyone wants to stick around and ask questions, feel free to do so.
After Sandy, Orton's data was used in modeling to see what New York would look like with 6 feet of sea level rise by 2100.
So this is a satellite map showing New York City without any flooding. Shown here is Broad Channel, the Rockaways, Lower Manhattan, and over here is Staten Island. If you get 6 feet of sea level rise, the everyday average high tide is going to start flooding a lot of neighborhoods. It's high tide in 2100. This is now showing tidal flooding of places like South Street Seaport, Lower Manhattan, a lot of flooding around Jamaica Bay, also on Staten Island. Hundreds of thousands of people being flooded at that point. It's uninhabitable when you start getting flooded so many times per year. That's tidal flooding, but then there's also storm surges. We can also look at what 2100 would hold if we had a very severe storm like Hurricane Sandy, plus 6 feet of sea level rise. A much larger percentage of the coastal zone is flooded. The west side of Manhattan, the Tribeca district, Wall Street, Battery Park, Lower East Side.
Sandy flooded 51 square miles, 17% of the city. With 6 feet of sea rise, those numbers would be closer to 100 square miles, or about a third of the city underwater.
This kind of flooding would be catastrophic. There's massive infrastructural elements for a city of 8 million people that are in the flood zones. Transportation system, the tunnels, the subways, the electrical system, and of course a lot of these things were flooded just by Hurricane Sandy, so if you envision 6 feet of sea level rise, then a great deal more is at risk at that point. The whole city could be disabled in this kind of flood scenario.
I don't think there's a one-size-fits-all answer to whether we should build or not in the floodplain. There's hundreds of thousands of people in New York City that live in floodplains. And I think there are probably some cases where it just simply doesn't make sense, where it's not just a floodplain, it's a highly vulnerable floodplain. Retreat in that instance might make sense.
What this means for the future, it means seawall or levee protection, storm surge barriers, or the city could encourage more building and population on higher ground and do things to try to discourage or buy people out who are in these low-lying flooded areas.
There are some clear statistics out there that for every dollar we invest in risk reduction, that there's a $4 avoided future cost. Sandy was a $19 billion event in terms of damages and lost economic activity. From the risks of climate change, that same event in the 2050s could be a $90 billion event.
I think we have to prepare for the unexpected. And what that means is, how do you create a city that can recover from any number of tough things happening to it, whether it's a flood or a tornado or a terrorist attack? Cities are vulnerable. Cities have always been vulnerable. Cities also have this extraordinary way of being resilient and building back. And so, to me, it's always about the basics: mobility, power, water. Fixing this is not rocket science, right? It's simply a question of will.